Hello, I'm Josh Udemeyer from the University of Texas at Dallas, and today I'm excited to present PyLingual, towards perfect decompilation of evolving high-level languages. Python is the most popular programming language in the world. Malware and products written in Python are often distributed as compiled packaged executables, which has driven demand for Python decompilation, demand that has been underserved by existing Python decompilers. To help fill this gap, we made our prototype implementation of the PyLingual Python decompiler available through a free online web service. Over the past year, we have seen a steadily increasing stream of Python bytecode decompilation requests. PyLingual now decompiles hundreds of Python bytecode files every day. This success was made possible through community engagement at events such as PyCon US and Black Hat USA, where we gave talks on Python decompilation and connected directly with real-world Python reverse engineers. Listening to and learning from community feedback, we were able to execute a well-received open source code release, opening the door for further community involvement. By providing verifiable decompilation support for modern Python versions, PyLingual has become an indispensable tool in recent threat investigations of Python malware, with more and more reports directly citing PyLingual as a key component of their Python analysis workflow. Moving forward, we will continue to support and improve PyLingual for the benefit of the Python reversing community. PyLingual delivers on an ambitious decompiler design philosophy centered on rigorous output verification, aiming to address the unique challenges of Python decompilation. The success of PyLingual's design, development, and deployment has been driven by the pursuit of perfect decompilation. Perfect decompilation is a statically verifiable test of decompilation accuracy that provides semantic equivalence guarantees without requiring knowledge of the original source code. A decompiled source is perfect if compiling it with the original bytecode's compiler yields identical bytecode. For each code object in a Python bytecode file, we test that each instruction and semantically important metadata table match exactly with those of the original. This verification step is separate from and independent of the decompilation process and provides the foundation for measurably improving decompilation outcomes. By maximally leveraging perfect decompilation to verify every decompiler output, we free the decompiler from needing to be correct by construction, shifting the burden of gaining user trust from the decompiler to the verification step. This way, perfect decompilation unlocks a huge design space for experimental decompilers. In PyLingual's framework, any mechanism to produce source code can act as a decompiler. The quality of a decompiler is determined by its ability to produce perfectly decompiled source code. But why do we need this much flexibility for the decompiler's design? Because Python's bytecode demands it. The core Python dev team prioritizes language evolution and flexibility over bytecode stability, and intentionally makes no forwards or backwards compatibility guarantees at the bytecode level. Every year, a new Python version introduces several new instructions in blue, as well as modifies the existing instructions in green. Python 3.11 even completely overhauled the exception handling mechanism by moving that control flow information from the instruction area to a brand new metadata table. This bytecode instability is separate from and compounds with constantly improving compiler optimizations. Coping with the lack of cross-version invariance is the core design challenge of Python decompilation. To address this challenge, PyLingual adopts a hybrid decompiler architecture that integrates statistical machine learning components with traditional program analysis techniques by dividing decompilation into three distinct subtasks: bytecode segmentation, statement translation, and control flow reconstruction. In general, PyLingual uses version-specific machine learning components for unstable, high-frequency details and relies on programmatic analysis for stable abstractions. To illustrate PyLingual's workflow, we will quickly run through a toy example, starting with bytecode segmentation. The segmentation model classifies each instruction in context as the beginning of a statement, internal to a statement, or the end of a statement. This establishes an association between the original bytecode and the to-be translated source code statements that will be used throughout the decompilation process. Next, the translation model translates each statement of bytecode into a corresponding statement of source code. We use a few pre-processing tricks to boost the accuracy and capacity of this translator, which are detailed in the paper. The first step in control flow reconstruction is to create a control flow graph. This is reliable in Python because Python's bytecode contains no indirect jumps, and code object entry and exit points are well defined. Then, using the statement associations from earlier, we attach each source code statement to the basic block containing its first instruction. Finally, we assemble the source code statements according to the control flow graph. The exact mechanism and heuristics that we used are discussed in the paper, and this is an active area of development and improvement in the open source code release. In PyLingual's framework, the quality of a decompiler is determined by its ability to produce perfectly decompiled source code. In one of many evaluations of the paper, we compiled 3,000 source code files from the Python package index in Python versions 3.6 through 3.12, then decompiled them with PyLingual and popular existing Python decompilers, Uncompile 6, Decompile 3, and PyCDC. Uncompile 6 and Decompile 3 use expertly crafted bytecode grammars for decompilation, but their support currently only extends until Python 3.8, leaving them 5 years behind Python's release cycle. PyCDC uses top-of-stack tracking to conservatively decompile simple bytecode sequences, improving version coverage at the cost of completeness. In all evaluations, PyLingual perfectly decompiled more bytecode files than all other Python decompilers. Building on PyLingual's success, we have 2 research thrusts planned for the immediate future. We are currently running user studies and will be hosting a tutorial session at this year's upcoming PLDI conference to explore human-in-the-loop decompilation. In this workflow, a human operator iteratively refines imperfectly decompiled source code until it passes the equivalence test. We're developing error localization methods and differential analysis tooling to minimize the expertise and effort required from the operator. Further, to leverage the over 130,000 Python bytecode files that have been uploaded to PyLingual's online service, we will conduct a large-scale study of Python malware and obfuscation techniques. So far, over 2,000 of the uploaded bytecode samples have been confirmed as malicious by VirusTotal, and over 500 samples use PyArmor for sophisticated obfuscation. Our aim is to identify previously unexplored Python malware and developed automatic reversing techniques for popular Python obfuscators. Thank you for your time and attention. You can try our online demo at pylingual.io or find our code at github.com/sysecutd/pylingual. Thank you so much.